So far we have discussed a fair amount of the processes like distillation, stripping, absorption, rectification and things like that. And most of these have a vapor liquid contacting and an arrangement has to be done. Since we are focusing on the equilibrium based approach, our approach here so far has been to find out how many ideal stages are required for a particular separation, and this is the stage what we are going to discuss today, is how to implement these stages in reality. In fact, what we are talking about is tower and tower internals, and when we are talking about the tower and tower internals, we must define one more thing also, that we will be using the term tower and column interchangeably. Both are used and both are equally popular. So, what I do now is I move on to the tower and tower internals, and we start with a little bit of recapitulation. We talked about the mass transfer coefficient. The mass transfer coefficient denoted by K subscript L. That means it simply shows that it is based on the liquid phase. We also had a term K L into A, that means it is a multiplication of A, which is a specific area, and A is basically is meter square per meter cube of equipment volume or phase volume, or whatever is the total volume of the system. And the mass transfer coefficient depends on basically on K L, and we can improve by improving A as well. That is what I wanted to emphasize at this particular point. We also have to have an idea that the controlling mass transfer rate, and we are talking about the phase 1 to phase 2 mass transfer. So, the mass transfer takes place from the left to the right. If I have a concentration of a component in C1 and if it is C2 here, it is the driving force is basically the concentration difference between these two. In fact, that is not the exactly the one. What you will find is there will be the interface here, there will be a concentration in the bulk which is fairly constant, then the boundary layer starts and it drips here. Similarly, for the phase, this is my phase 1, this is my phase 2, you will also have a boundary layer here which is having the bulk concentration here, the phase 1 is having the bulk concentration here, and definitely the concentration difference drives the mass transfer. Now, there is one thing very clear we have to make, that means that resistance to mass transfer lies in this boundary layer, Now, it is possible that both the resistances are, in fact, here what you find is both the resistances are in series. If this is R1 and this is R2, the net effect is R1 plus R2. It is possible that one particular phase resistance is much smaller as compared to the other one. What will happen? It will make either this one tending to 0 with respect to the other to a very small number, and we can neglect. So, in that case R will be nearly equal to either R1 or the R2. So, what is very clear to us right now, that there will be possibly, in case of interface mass transfer, one of the side resistance which could be the liquid phase side or the gas phase side or the vapor phase side, whatever we may call it, will be controlling. Now, we think of the mass transfer and implementing the mass transfer. The implementing the mass transfer is definitely by contacting the liquid and the gas phases. Well, if it is a liquid-liquid system, it will be liquid-liquid phase contacting also, but after all the phases through across which the mass transfer happens has to be contacted, And we know one thing, the more intimate contact we can make, lower will be the resistance, because with turbulence the boundary layer thins out. So, naturally it offers less resistance, and quite naturally what you have in that case is a better mass transfer, which is basically KL. There is another thing you have to do. Even if it diffuses from one phase to the other, in order to go to the bulk, it has to move. It has to move over a distance. It starts from here and it has to move here, and this also is a path in which there is a resistance. It is not that it just goes and enters the interface and just at the interface of the second phase, but it from there it has to diffuse to the bulk. So, this is basically, suppose we have a length in which across which it has to diffuse, and somehow we can reduce this, then we are going to help the mass transfer. That means, the mass transfer rate is going to be improving by this action. So, what we have here right now is a case in which we think of dispersing one phase into a continuous phase. So, any mass transfer equipment that we talk about, interface mass transfer equipment, will definitely involve a good amount of agitation, and it will also try to enhance the mass transfer by dispersing one phase into a continuous phase. Now, depending on which phase offers the higher resistance, you decide the phase to be dispersed. This is more true in case of liquid-liquid. It is true in case of a little bit to some extent in case of vapor-liquid also, but mainly the type of contactor that you decide for your mass transfer depends on which phase the controlling resistance to mass transfer resides. Now, we are talking about towers or columns. We have done analysis of continuous systems, and in continuous systems like a distillation, what we have said that there are different stages of contacting. So, definitely there are different stages of contacting, but it is not essential that you will always have such stages. You can have a continuous contacting also. For example, if you have a packed bed, which I am showing here, through which you have a gas going up and a liquid coming down from the top, and there will be, if I consider any particular section, you will find there is an upflow of gas and a downflow of liquid here in this particular section, and there is a fair amount of interaction between the two phases. So, what I would like to say is, at this particular point, your continuous contacting will be offered by packed beds. So, your continuous contacting is definitely, the equipment is going to be packed bed for you. And the tray towers, we will see the details of the tray towers, are stage wise contacting equipment. Well, there are different types of contacting equipment, and so far you have come across mainly the vapor liquid contacting requirement of distillation, absorption, stripping, and in case of adsorption you have gas solid contact. Now, I repeat once more that we are going to use the term tower and column to be equivalent. What are they used for? They are used for realizing multi-stage contacting. That means, in the same piece of equipment, you are expected to provide more than one ideal stage of contacting. Now, so far we already have seen in case of heat transfer class or in mass transfer class that counter flow gives you in case of contacting of two species, a higher driving force. Let us see what all arrangements you have. You also have here a co-current flow, but co-current flow is not normally there in this type of tray contactors. You will find co-current flow in case of Venturi scrubbers only. Which is also a vapor liquid contacting equipment. Now, let us see. Ideally, my equipment should be a counter flow, because it is expected to generate a higher concentration gradient, and with that you get a higher mass transfer in the same equipment itself. We always have been drawing our contactant like this. You will have a gas flow, the gas goes out, you have a liquid flow, and the liquid falls down here. It could be packed, it could be trays. What you have so far drawn are these are distinct trays, and ideal tray is one in which the leaving streams, the leaving, I should have drawn it here in this part. So, what I draw is, I draw with a different pen perhaps. So, what I draw here is basically the gas leaving and the liquid leaving, these two will be in equilibrium. This stream and this stream. So, what we do now is basically we talk about how to implement these in real life. We are talking about tray towers. If you look at tray towers, the tray towers often in your mass transfer class you have drawn the tray tower to be like this. You have been told possibly that you have a tray, and from the tray over the tray there is a liquid which falls from the upper tray, and it moves like this. It moves in this direction, and in this direction. The gas from the lower tray, or the vapor from the lower tray, penetrates through this liquid column and it goes up. Now, if you look at this particular type of contacting, what you find is here is the liquid flow and here is your gas flow. So, what type of contacting it is? It is basically a cross flow. So, on a tray there is a cross flow, except in one type of tray. Those trays are basically sieve trays without downcomer. So, that is the type of counter flow tray. Now, how it looks? It looks very simple. You have a perforated sheet functioning as a contacting device. You have a hole here, you have a small little bit of liquid which showers down through these holes, and through the same hole you have a counterflowing gas or vapor liquid. So, basically you have a hole through which you have the gas going up as well as the liquid falling. So, this is a situation in which you have basically counter flow. This is your sieve tray, and in such cases, since the liquid falls through the tray itself, you do not require a downcomer. It is too obvious. Now, the question comes that if this be the case, how do we manage in case we have to have a counter flow arrangement? If we really have to have a counter flow arrangement, how do we achieve it in a tray?
This is done also in a very nice way. You have one tray here, you have a second tray here. You have a downcomer which comes down, sorry, it does not come, okay. The downcomer comes down. The upper downcomer ends here, the liquid flows across this and falls to the lower tray. And this is your gas stream and this is your liquid stream. Now, you have such trays placed one above the other. That means, in the tray, the part of the liquid which comes from the top is something like this. And finally, it comes out. The part of the gas is rather direct. It passes through each of these liquid streams, it bubbles through the liquid streams and goes up. So, what you find here in the tray tower, even you have, though you have cross flow in individual trays, the overall tray offers a counter current arrangement. Now, we look at what are the other tray arrangements possible. So, we have some idea about the tray towers now. We think about the pack tower, which we also have said specifically that pack towers will be definitely be the typical counter flow arrangement. And if we look at the other ways of conducting, I can also have a spray tower. I could have my liquids being sprayed inside a tower. My liquid comes in, it gets sprayed, and I have my gas counter currently flowing in that particular tower, and it becomes a spray tower. Exactly in the same way, we could also have a bubble column also. That means, I have a liquid filled with, I have a tower filled with liquid, I have a distributor for my vapor or gas, and the bubbles go up, and I make up this particular liquid, I bring in liquid and my liquid goes out. So, what you find here, the bubble columns are cross flow, spray towers are cross flow, pack towers are cross flow, tray towers overall they are cross flow, but individual, sorry, I made a mistake. I should have said that both pack towers, spray tower and bubble columns, they all are counter flow towers, whereas the tray individual trays are cross flow, the overall the tower is a counter flow. We will look at the tray tower and the pack tower general arrangement. We talked about dispersing one phase into the other. Conventionally, in tray towers, the vapor is dispersed, and depending on the type of arrangement we have for the dispersal, it will be a sieve tower, which means you just have a hole, a bubble, it could be a bubble cap, where you have an inverted cup like structure over a nozzle or a riser, or it could be valves which has got a movable part also. Now, each of these type of trays have their own advantages and limitations. If we look at all the towers, what are the things common? The first thing is we can have a look at the trays are fixed. That means, we are talking right now about the tray deck. That means, if you are talking about a tray tray is basically the deck on which the vapor disperser is arranged. The tray normally will be fixed to the tower. It usually is bolted to a support ring. We will look at the details of each of these with drawing later on, but right now what I would like to say is, if I take a section of my tower and look from the top, what you will normally have is a tray like this. That means there will be a segment which will be missing here. You do not have this part. It is a disc. So, on this disc you have the fitment of your vapor dispersers. There is another place here or another section here which has got no holes or no dispersers. So, you have dispersers only in this particular section. The liquid from the upper tray falls here through the downcomer, then it travels from the left to the right, and since this portion is missing, it falls off. So, your tray deck, if you are talking about in case of a cross flow tray like this is basically your tray deck shape, which is this. Now, what I do is I would like to fix this onto my tower. How can I do it? If I look at the tower section itself, and if I weld a ring, here, and on that I place my tray, that the ring is all through, and I bolt it here. That means I will have bolting here at this point, I will have bolting here at this point, 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 and it does not exist. So, there is no question of any bolting here. So, these are the bolts, and this tray ring will be usually welded to the shell, and on the tray support ring, which is the tray support ring here, your tray deck will be bolted. Now, you understand one more thing here also. We look at the other arrangements which is there on tray towers, apart from the vapor dispersers. It does have to have a downcomer, it must have a downcomer. You are expected to have a level of liquid because your liquid flows across this. So, definitely you would like to have a particular level of liquid on your tray, and in order to ensure that you have a level of liquid on your tray, what you provide here is a weir. It is nothing but like a dam, and over the dam the liquid flows down. This way. To where does it go? It goes to the downcomer. This part is the downcomer of the tray. Where it comes from? It comes from the upper tray. It comes from the downcomer of the upper tray. It cross flows like this, flows over the weir and comes here. Now, we try to see that whenever we have been drawing in mass transfer class and drawing schematics of vapor liquid contacting or distillation trays, we have very often referred to this arrangement. These are the trays, this is the tray deck, and this portion is the downcomer. It is obvious that in this case also what you find, the liquid falling from this tray will be taking a path like this and finally coming to the bottom. What will happen to the vapor which goes up? The vapor will flow through this, it will flow through this, it will flow through this, it will flow through this and go up. So, this is what I wanted to show you earlier, and you will notice here that your tray will have quite a few connections. One is for your feed, definitely. The other is for the reflux, which is to be given on the top tray, tray number 1. There will be a nozzle which will be taking out the overhead vapor. The bottom product has to be taken out. Possibly there will be one more outlet which will be taking the bottom liquid to the reboiler, and there has to be a nozzle which will be feeding in the reboiled vapor here. Below the feed section, you already know that it is a stripping section. Above it, it is a rectification section. Now, with this, we look at the similarity between the packed tower and the tray tower. The only difference that you will be finding here is you have a packed bed. Instead of so many trays in the rectification section, you have a packed bed. Similarly, the trays in the stripping section, instead of having trays here, you have another packed bed. Now, there is a feeding section also, feed section also. Your feed will, in most of the cases, will be either liquid or a mixture of vapor and liquid. So, what you expect is, after the liquid enters, it has to be distributed. This is something which is very typical. It should be distributed fairly evenly on the bed itself. So, you have to have a liquid distributor, which is absolutely important, because the quality of distribution will define how much of efficiency of contacting you are going to have here. If you have poor distribution, your contacting will be poor and your efficiency will be less. Exactly the same problem you will also face in case of the reflux which is introduced. In fact, any liquid which is introduced into a packed tray has to have an arrangement for distribution. It could be a pressure distributor as shown here, it could be a gravity distributor, which is schematically shown here as well. On the top, we expect only the vapor to go out, but where does it go out from? It goes out from the top tray. So, what happens is, basically the liquid droplets will also get carried over, and above the top tray, even above the reflux, before the vapor goes out, what you have is a demister. The demister is nothing but a wire mesh. It is nothing but a wire mesh, typically around 100 millimeter. Thick wire mesh. So, that is your demister. What happens? The fine liquid droplets hit this and they get stuck, and later on when the layer grows, it falls off. In case of a bed, definitely you have to have two more things. You have to support your packing. So, there has to be a packing support, which is usually a grid, and there is a bed limiter also. You have the vapor coming up. Under no circumstance you want your top bed packing should be thrown off the bed. So, usually you will also have a grid here, or others than grid, you can often have some bigger size packing here on the top also, so that they do not get lifted, and this acts as the bed limiter. This is again basically the arrangement with a typical type of vapor disperser with which we will be contacting, and we will be learning the design of this. This disperser is the bubble cap disperser. What it is? It is nothing but it is nothing but a riser which is fitted to the tray, covered with an inverted cup. So, the vapor coming in here, the cup that you see here looks like this,
it will have slots. It will have usually square or trapezoidal slots here, through which the vapor bubbles will be coming out. So the vapor which is, or the gas which goes here, it comes out through these slots. You have the slots here, and the entire thing is dipped in liquid. This is dipped in liquid, so the bubbles form and they go up. The passage of the liquid has been shown here. The liquid from the upper tray falls to this particular tray. It comes out through this, through the bottom of your downcomer, flows over the bubble caps. The bubble caps remain immersed, goes through the downcomer and goes through the next tray. It is obvious that on such a tray you do not provide the disperser everywhere. When it comes out of the downcomer and when it is going to face the outlet wear, what you do normally is you leave some space here, which are known as the coming zones. All these will be detailed when you go for the design of the bubble cap trays. Here what you have is basically the diagram of a bubble cap tray. The different type of bubble cap trays which are used in industry are given here. You can understand this is the complete tray, this part of it is the downcomer. These are basically the vapor dispersers in the form of bubble cap. Though we have said a bubble cap should look like just a cap, there are different shapes. It is not essential that it will have a circular shape. It could be a rectangular one also, or something similar to that. So, beyond this, what we see is the other type of disperser. The other type of disperser is basically the valve type. The valve type means basically what you have in this case is a flat disc. The flat disc, if it sits on this hole, it will leave it closed. So, and you have the gas which is pushing it up and it is immersed in liquid, and the gas goes like this, forms bubbles and it comes out. Now, if I just leave my disc here, this will be this will get shifted any moment. So, what is done is it is given 3 legs which are bent outside, So, what happens is initially your disc is here with the legs like this. After, and I have started my gas, and when it increases, when the flow increases, it gets lifted up. So, what happens here in that case? It gets limited by the length of the leg. So, what we have here is just a plan how it looks like, and here is an elevation or a side view, whatever you may call, which shows that the legs are there to hold it inside the hole so that it does not jump out, and this is basically the 2 type of contactors or dispersers that we are going to learn how to design. When we talk about the different sections of a tray or pack tower, we have to have the details of different sections. We focus on different sections, and basically we have divided the sections which are common for all types of dispersers, and in case of pack tower also. You have to focus on the tower top, which will contain the overhead exit and the reflux entry arrangement. You will have the feed section which will have the feed entry nozzle and the distribution of the liquid. In the bottom section, the bottom liquid will be sent to the reboiler.
it will also go to the pump to be sent out as a product stream. In the bottom section, there has to be a vapor entry to the column which is coming from the deboiler itself. There are some columns which offer a side stream draw facility also. So, side stream draws definitely have to be covered, and that is a section where, and it is a special type of tray and it is a special type of arrangement which we will learn immediately after this. And such things are required not only in case of side stream draws, in case you have circulating refluxes. Circulating refluxes, in most of the common columns you do not require, but circulating refluxes are there in the large columns like in the crude distillation unit. In case of packing, we already have said that liquid distribution is absolutely important. So, if you really have a pack tower which is fairly tall, to avoid any sort of channeling, you have to distribute the liquid. So, wherever you have a liquid distribution zone, how it is done, what exactly is the physical arrangement, we will have a look. I think with this I will stop here today, and we will start in the next class with a typical tray construction. Thank you.